Welcome to another episode of I Am Nano.
Putting the I in I Am Nano, I am your host, Irfani.
And I am your other host, putting the M, Monica.
In today's lit update, we will be talking about your house windows. Actually, not just that, all the surfaces in your house.
What? Irfani, why are we talking about this?
Well, we need to know how your house surfaces can grow bacteria or emit chemicals.
Yes. And then we'll be more aware to clean our houses more often.
Yes, exactly. So scientists at University of California, San Diego, and University of Texas particularly looked at the effect of cooking on the formation of organic thin films on glass surfaces. They're interested in understanding how water adheres to these films.
The water is what catalyzes the bacterial growth and chemical reactions.
Exactly, right. So they tested two categories of samples: glasses that were exposed to a simulated stir frying activity, and then glasses that were left in a kitchen for 3 months in a Texan house.
And now the researchers used the atomic force microscopy technique to look at the shapes and sizes of the droplets on these surfaces, as well as infrared spectroscopy to further understand the chemical composition of the molecules. And they found that the activity of stir frying deposited submicron and flat particles. When the researchers placed the samples in a high humidity environment, these droplets increased in size. On the other hand, the droplets from the 3-month samples were supermicron sized, and the increased humidity is higher on the droplet edges.
Mm-hmm. And these droplets are composed of semi-volatile hydrophobic organic compounds such as fatty acids. Now, a common organic compound that is emitted during cooking is oleic acid, which is found in olive oil. And I use olive oil pretty much every time I cook.
Yeah. Oh, yummy. Yeah. Yes, me too.
Yeah. So when we cook olive oil, these oleic acids will form a thin film on surfaces such as glass. And when they're exposed to the environment, the molecules in the air can react with it and then change the film's composition. So ozone is the chemical that they were interested in looking at. And when oleic acid react with ozone, it forms into nonanoic acid, which is a shorter fatty acid chain than oleic acid.
And it is because oleic acid has a double carbon-carbon bond that makes it reactive to oxidants. These are chemicals that take electrons from other chemicals. They just go around taking electrons, similar to how pirates plunder treasure.
Yeah, exactly. That's very true. Anyway, so they looked at these two molecules, the oleic acid and the nonanoic acid, as well as their sodium salts as comparison. And when they looked at the infrared spectra of these samples, they found that the stir-fried samples were mainly composed of the sodium nonanoic acid, while the 3 months kitchen samples had a mixture of sodium carboxylate salts and other oleic and nonanoic acids. Since they were exposed to the environment for 3 months, though, it's really hard to really determine the specific chemical composition.
And also to add, an interesting observation in the paper is how these compounds uptake water. Now, hygroscopicity is the term used to determine a compound, molecules, or anything really's ability to uptake water. So how do they capture water? Because they are organic compounds and they don't mix with water quite easily. That's a known fact. So water really forms on the edges of the oleic acid in this case, and these water puddles per se form water bridges with the neighboring droplets. When the oleic acid is oxidized under wet conditions, it does attract water more easily.
Mm-hmm. But compared to oleic acid, the oleic acid sodium salt is definitely more hygroscopic and can form thin water films, which then can grow when exposed to higher humidity environment. And so based on these findings, the glass wetness definitely is highly dependent on the fatty acids deposited on them.
Interesting. And another fun observation is that smaller sized particles found in the stir frying samples are more hygroscopic than supermicron sized particles.
Yeah. So, it's really cool to observe and understand how these organic compounds, oil essentially, can attract water on surfaces, either after being exposed to the air after a long time, and then it changes into a different compound that's, more hygroscopic. And also at high humidity, it becomes really wet, the surface. They did the test at 80% humidity though, and most houses and rooms have a maximum of 60% humidity, but it's still definitely a good insight.
Oh, yeah, for sure.
Yeah.
And this is going to make me clean up way more than I usually do now that I
Yeah.
know this.
For sure. And keep in mind, this is just for houses. What about restaurants? They cook pretty much all day long. And I'm sure they clean the counters, but not sure about the windows and walls. They don't clean them, I don't think, as frequently.
Yeah, that's a great point. Oh man, I
Uh-huh.
didn't even think of that. Oh, who
Yeah.
knows?
Well, I mean, hopefully health regulations will change later once we really understand more how the effect of, these water films form, how it affects, bacteria growth and chemical emitted out of the walls. But we'll have to do more research on that. All right, that is all the nano for today. Take care.
And stay curious.